So solution dilution. We often store chemicals as solutions in the stockroom in a more concentrated form than what we need for an experiment. This is convenient because we can use that stock solution to make lots of different concentrations, and it takes up less space than a dilute solution, which has got a lot of water in it. This is similar to buying concentrated frozen orange juice at the grocery store. Instead of a big gallon of frozen orange juice, it's a small can. And when you need to use it, you put the concentrate into a pitcher and you add water. That's diluting the concentrated solution. And that's what we do in chemistry as well. So it's important to understand that when you dilute a solution, the amount of solute doesn't change. Only the volume changes. So think about the orange juice. In that can of frozen orange juice, there's a certain amount of orange goodness, right? When you pour that into a pitcher and add water to it, does it change the amount of orange goodness in the pitcher? No, it's the same amount of orange stuff, right? We're just adding water to it. That's what we're doing when we're diluting solutions. And if you can really grasp that, it helps you to understand what all this business with the calculations is about. So the moles of solute that are in the concentrated solution are equal to the moles of solute in the dilute solution. And so we can use that to get this equation. M1V1 equals M2V2. Very useful equation. M here stands for molarity and V stands for volume. So the molarity of the first solution times its volume would give you the moles of solute. And that's going to be equal to the molarity of the second solution times its volume. Now I want to warn you about something. Students try to use this when they're doing stoichiometry calculations, when they're doing titration calculations, and sometimes people who should know better will tell you to do this. Don't do it. It's very, very dangerous. What's especially dangerous about it is that sometimes it works. Okay, sometimes it works. If the stoichiometry is 1-to-1, it works. But often the stoichiometry is not 1-to-1, and I will try to trick you with that on an exam. Okay? You've heard me say I won't try to trick you. This is one I will try to trick you on, okay? So you've been warned, then it's not really a trick, is it? So here's an illustration of how we might dilute a solution. We're going to be doing this in lab today. So here we're taking 0.15 liters of a 10 molar stock solution, and we're putting it into a volumetric flask. Volumetric flasks are designed to contain a specific volume of solution. So we put that in there, and then we're going to add some water, mix it up, and then continue to add water until we get the meniscus at the bottom of the line. Then we have to stopper it and invert many, many times to mix it thoroughly. Down here at the bottom, we can look at what's going on with the concentrations. So if we have 10 moles per liter and we multiply by the volume, 0.150 liters, that means that we have, come on pointer, 1.5 moles of solute that we added into the flask. So that's like taking the orange juice concentrate and pouring it into the pitcher. Now we're going to add water. You fill up the can 3 times and you pour it into the pitcher. The amount of stuff, the amount of solute is the same. It's just a larger volume and a lower concentration. So now the concentration is 0.5 moles per liter. The volume is 3 liters. We multiply those, we get the same number of moles. Okay? When you dilute a solution, the volume gets bigger, the concentration gets lower. So let's look at how we might do a calculation. To what volume in milliliters should you dilute 100 milliliters of a 5 molar calcium chloride solution to obtain a 0.75 molar calcium chloride solution? So I mentioned students like this dilution equation. So how do you know when it's okay to use that? Well, here's the word dilute. If you see that, you're good. The other thing to look for here is this is calcium chloride and this is calcium chloride. It's the same solute. There's no chemical reaction occurring here, so we can use the dilution equation. So let's write that down. M1 V1 equals M2 V2. And I like that it's 1s and 2s instead of C's and D's for concentrated and dilute, because it doesn't matter which one you call solution 1 and which one you call solution 2, as long as you pair the concentrations and the volumes appropriately. So that's the equation we're going to use. Let's pull the numbers out, write them down, and identify what they are. So I've got 100 milliliters, and I've got 5.00 capital M. Let's write down what the capital M means. That means moles divided by liters. And then I've got 0.750 capital M. And again, let's express that as a vertical fraction. So from the units, we should be able to identify that this is a concentration, a molarity, and this is a molarity, and this is a volume. So I've got volume, I've got molarity, I've got molarity. Now we need to pair them up. So that we have one volume, we're looking for another volume. Which molarity goes with this volume? The 5, right? 100 milliliters of 5 molar. Those two go together. I'm going to call them 1. So that's V1, and this is M1. So the other molarity then is going to be M2. So I've identified the volumes, the molarities, and now I can look at my equation. This equation has 4 variables in it. I've been given 3. I need to find the 4th. So I'm looking for V2. So that means I need to rearrange this equation. I need to solve it for V2. So I'm going to divide both sides by M2. So M2 over M2 cancels out. And now on this other side, I've got M1 V1 over M2. So V2 equals M1 V1 over M2. I'm going to skip underlining them. Some of you, I could tell from one of the questions on the exam, need to work a little bit on your rearranging equation skills. Okay, that's going to come up over and over again. So the time to fix that is now. I can help you with that. Chris can help you with that. Just a little bit of algebra goes a long way in this class. So we've got M1, we've got V1, we've got M2. Let's plug them into this equation. Always include the units. So M1 is first. So M1 is 5.00 moles per liter. Make that a vertical fraction. When you make it horizontal with a slanted line, you'll lose your minds and you do crazy things that are wrong and you get the wrong answers. So 5 moles per liter, and the volume one is 100 milliliters. 100.0 milliliters. And then all of that is divided by M2, 0.750 moles over liters. Before you do the math, check the units and make sure things are going okay. Here I've got liters and this is milliliters, but look what's going to happen. I have liters, moles per liter in the numerator and moles per liter in the denominator. They cancel out, right? So this mole cancels that mole and this liter cancels that liter. If you need help understanding compound fractions where you have fractions in the numerator and fractions in the denominator and what to do with them, ask me. I can help you with that. So the units cancel out, and the unit that's left is milliliters, and ta-da, that is what they're asking us for. So now we just need to do the math. So we have 5, well, my calculator's doing something strange. 5 times 100 divided by 0.75 equals, my calculator's going to give me this ridiculous number, 666.666 repeating. The units would be milliliters. We need to pay attention to significant figures. So here I've got 3 sig figs. This one has 4, and this one has 3. I'm just multiplying and dividing, so I go with the fewest number of significant figures. My answer should have 3 significant figures. I underline the last one I'm going to keep, and the next digit tells me whether to round up or down. Some of you are doing some funny things in your lab reports where you underline this and then you report it to that digit. I don't know what's going on, but it's not right. So this is going to be 667 milliliters. It's awesome if you can then look at your answer and try to picture the situation to see if it makes sense. So if I'm going to take 100 milliliters of this 5 molar solution, a small volume of the concentrated, and I'm going to make it more dilute, that means the volume should get bigger. And my volume got bigger. A common problem is to get your 1s and 2s backwards, and it ends up getting smaller. So then you're taking the orange juice concentrate, you're pouring it into the pitcher, you're adding water, and it's getting smaller. That doesn't work, right? Any questions? So we can use molarity in stoichiometry. So this is going to be a variation on grams to moles to grams. Molarity is one of our favorite concentration units in chemistry because it relates the volume to the moles of stuff. And what do we need in stoichiometry? We need to know the moles because that's what the chemical equation tells us about. So the general concept, the general plan for solution stoichiometry problems, instead of grams here, would be a volume. So we're doing solutions here instead of pure substances. So a volume of A to moles of A to moles of B to volume of B. So this is variation on a theme here. So before we had grams of A and we went to moles, and then we went back to grams of B at the end. Now we have different options. So some problems will go straight across like this, volume, moles, moles, volume. You might have grams to moles to moles to volume. You could have volume to moles to grams, all sorts of possibilities. That's why it's important to understand the process of doing these problems because there are way too many variations for you to memorize how to do them. So here's an example. What volume in milliliters of a 0.150 molar nitric acid solution will completely react with 35.7 milliliters of a 0.108 molar sodium carbonate solution according to the following balanced chemical equation? So I'm going to use my numbers, I'm going to use the equation to organize the information I've been given. So I've got a concentration, 0.150 molar HNO3. So I find HNO3, and I'm going to write 0.150. I'm not going to write the capital M. I'm going to write moles divided by liters. And then I'm told I have 35.7 milliliters of the sodium carbonate. And I'm given a concentration of that as well, 0.108 moles over liters. So I've got all my numbers written down, then I'm going to look for the question, what volume in milliliters of the HNO3? So my question goes here, and the unit requested is milliliters. When a unit is requested, you have to give it in that unit. That's what caused the Mars orbiter to crash. They gave the number and wrong unit. Thankfully, the stakes are not that high for this class. We'd be in trouble. Okay, so our general path for stoichiometry was grams to moles to grams. That's still a great place to start. I'm looking here and I've been given milliliters. So at the beginning, instead of grams, I'm going to have milliliters. And then at the end, it asks for milliliters, and so I'm going to do milliliters at the end instead of grams. Now, this is a situation that comes up a lot. We've got a volume in milliliters because milliliter is a convenient unit for the smaller quantities of stuff that we use in the lab. We don't do experiments where we put in 2 liters of stuff. So usually these are in milliliters. The unit for molarity is always moles per liter. So we've got this issue here with milliliters and liters. And there's like 3 different approaches you could take to taking care of that. So then, yeah, I never think ahead because that's boring. So I'm on the spot right now trying to think which one should I share with them. So we're going to start here. We're starting with this one because this is the information, and we're going to this one. Volume of sodium carbonate to moles of sodium carbonate to moles of nitric acid to volume of nitric acid. Thank you. Love having the door open, but trains. I get comments on my YouTube videos. That's a really loud train. Yeah, it is. Really loud train. So from milliliters, I'm not going to deal with the milli part right now. I'm just going to get the rough thing in here. So I want to go from volume to moles. So this will be moles of nitric acid. And then I want to go to moles of the other thing. Oh, do you see what I did wrong here? What did I do wrong? I got the wrong chemical formula here. This is nitric acid is what I'm trying to find. This is the sodium carbonate. So that's not going to work. Let's fix that. So Na2CO3, and I screwed that up over here as well. Yeah, everybody makes mistakes. It's part of being human, so there's nothing to be embarrassed about. There we go. Now I want to go to moles of nitric acid. And then here, I wanted to go to milliliters. So milliliters of nitric acid, HNO3. So if I take this unit and put it down here, I'm going to have milliliters of sodium carbonate solution and moles of sodium carbonate solution and moles of HNO3. So I've got milliliters to cancel milliliters, but do I have information that gives me moles per milliliter? No, I've got moles per liter, right? So this maybe should be moles per liter, right? And then the liter doesn't cancel the milliliter. So I want to introduce you to my friend millimole. And I kind of teased you with one on the exam where there was a problem that had millimoles. You can take the prefix milli and stick it in front of any unit. You could have millifeet if you want to. People look at you weird. Millifeet. Well, that would be 10 to the minus third feet, right? So if I want milliliters down here, and I've got moles up here, and over here I've got moles per liter, if I put milli on both sides of the line, have I really changed anything? I put milli here and milli down there. The relationship is the same, right? So up here where I've got, actually, this is what I'm going to do. I'm going to just move this over a little bit. So here I have moles per liter. If I multiply the top by 10 to the minus third and the bottom by 10 to the minus third, is it still true? I did the same thing to the top and the bottom. So I'm just putting a milli on both sides. So milliliters, milliliters, millimoles. Okay, so now this works with that. Does that make sense? This is not the only way to do it. It's like the fast, elegant way. We'll do a slow, tedious way later. Here, moles to moles, well, that's not going to cancel with this, so would it be okay if I put milli on both sides of this fraction as well? Sure. And then over here, milliliters on top and millimoles on the bottom. I'm just throwing milli everywhere. So this is one approach, just embrace the milli, do it all in milli. The other way is to convert to liters and do everything in liters. Then you have to convert back to milliliters. So I did this like liters to moles to moles to liters, but I threw milli in front of everything. So millimoles per milliliter, that's the same as this concentration because I can do that up here as well. So that would be, and I don't have room for the numbers now, 0.108 millimoles of sodium carbonate solution per milliliter. Here in the middle, I've got my mole ratio. The mole ratio works in moles or millimoles, or you could do megamoles or all kinds of other things. 1 mole of sodium carbonate makes 2 moles of sodium nitrate. Why did I say that? I don't know. That's irrelevant. We're not looking at sodium nitrate. We're looking at this one. I need 1 mole of this for every 2 moles of nitric acid. So if I have 1 millimole of this, I need 2 millimoles. So HNO3 has a 2 in front of it, Na2CO3 has an implied 1. Then at the end here, I've got the molarity of the other thing. So again, let's just fix up this so it looks right. So that's what I was given, moles per liter. If I multiply the top and bottom of a fraction by the same thing, I haven't changed it. So I can put milli on top and the bottom. So then over here, I want 0.150 in the bottom. Well, what am I doing? I don't know what I'm doing. I'll put a little caret here, because I didn't leave space. 0.150 millimoles of that. So now milliliters cancel milliliters, millimoles cancel millimoles, millimoles cancel millimoles, and I'm left with milliliters. So 35.7 times 0.108 times 2 divided by 0.150 equals. The numbers that were given to me all had 3 sig figs. So my answer is going to have 3 sig figs. 51.408. And I'll round that to 51.4 milliliters. Yes?
If we didn't have the balance chemical equation, we could just use M1V1.
That's an excellent question. If we didn't have the balanced chemical equation, could we just use M1V1? No. It's very tempting, and people do it all the time, but you'll get the wrong answer. When you use M1V1, you lose this. So in this one, you'll be off by a factor of 2. So when we're looking at this, how do we know that we shouldn't use the dilution equation? So here we have a concentration of HNO3. Here we have a concentration of Na2CO3. They are not the same thing. If they were both HNO3, yes, use the dilution equation. But they're different compounds, so that tells us that there's a chemical reaction that has occurred. If you were not given the chemical reaction, you might have to write it and balance it yourself. Could happen. Excellent question. Any other questions?